So we'll start with questions. If anybody has any questions from the previous homework assignments. So take a moment, kind of look through your things. If there's anything you want to ask about before we dive ahead. Okay, that's all right. No big deal. We've had a bunch of time in class the last couple of days to work on this anyway, so not surprising if there's, not a lot of questions at this point. Totally okay with that. Hi, Evan. Today, what we're going to do is we're going to look at using matrices to solve systems. And we're going to look at 3 different approaches. So those 3 methods that we're going to look at are going to be using a matrix equation, something called Cramer's method, and a third thing called Gaussian elimination. All right, so let's just kind of look at an example here for a matrix equation situation. We'll talk about kind of how to do this and some of the finer points, but we'll do it kind of in the midst of doing an actual example problem. Okay? So let's say that we have actually, no, let's not do that. Sorry. Let's say we have this as our system. And now we'll kind of discovery approach this, and then at the end, we'll kind of summarize, like, without having to go through all the steps I'm about to do, what you would do to kind of get this matrix equation set up. But I'm going to take like a explanation-heavy route to get to the setup, and then we'll summarize after that, like how to go directly from the system to the matrix equation, where you wouldn't have to do this justification along the way. But I feel like it's probably a good idea to justify it to you, so you can see why what we're about to do works. rather than just like take my word for it. So what I'm going to do is I'm going to treat the left-hand side of this system as one matrix and the right-hand side as a second matrix. So this is a 1 by 2. I'm sorry, 2 by 1, and this is also a 2 by 1. And I know that it's okay to do this because for matrices to be equal, both sets of corresponding elements have to be equal, right? Which would be the same thing as if the system is true, right? That both equations would be true at the same time. Everybody's okay with that idea? What I'm going to do now is I'm going to break this 2 by 1 matrix into a 2 by 2 matrix times a 2 by 1 matrix. And that's certainly possible, right? Because a 2 by 2 times a 2 by 1 still gives us a 2 by 1. Everybody's okay with that idea? And what I want is my 2 by 1 matrix to have only variables in it, and my 2 by 2 matrix to have only numbers in it. So my 2 by 1 is just going to have x and y because those are the only variables that are in it. Look at the entry x minus y. I would have gotten that by multiplying this row to xy, correct? So that tells me then the x would have been multiplied by 1 and the y by negative 1. Is that okay with you guys? Then I'll look at the second row up here. I would have gotten that row or that entry by multiplying this row to the x, or to that column. So I would have multiplied the x by 7 and the y by negative 1. Now if I look at this, if I look at this matrix, and I look at this part of my system, what do you notice? The matrix is just the coefficients from our system in the exact same locations, right? We typically call this matrix the coefficients matrix. This guy we call the variables matrix. And this one we call the solutions matrix. Every system of equations we can formulate into a matrix equation using this same format, where we have a coefficients matrix times a variable matrix equals a solution matrix. So this is what we mean by a matrix equation. Is this guy right here. Everybody feel comfortable with how you could go directly from here to here? Again, I didn't want to go directly there without telling you a little bit of the story of why that's okay to do. But it's pretty easy to do it once you see it, right? Okay. Now, what I'm going to do for the interest of making life a little bit simpler is I'm going to refer to these matrices as A, X, and B. And I'm going to use their subscript as or their dimension as a subscript. And I'm going to solve this system now, or I'm going to solve this matrix equation with a, b, and x, and then when it gets to the x by itself, I'll go ahead and plug everything back in and kind of do the computation. But until I'm ready to kind of plug everything in, it's a lot less writing if I just refer to those as a, x, and b instead of writing out the whole matrix over and over and over again while we do this algebra. Is everybody okay with that idea? So again, we're wanting to get the matrix x by itself because we want to solve for the variables in it. So how would I get that matrix x by itself? Okay, well, let's ask this question instead to kind of get our minds jogging in the right direction. If I had equals 4, and this is just like regular algebra, how would you get the x by itself? You divide by 2, right? Now, is there matrix division? No. So we can't do dividing, but if I said, okay, how would I solve this equation, 2x equals 4, without dividing, what would you do? Multiply by 1/2 to both sides. Everybody okay? Now, what is the relationship between 2 and 1/2? Okay, they're reciprocals. Good. There's another that's true. And for real numbers, the reciprocal also has a special name. It's also called the multiplicative inverse. So if we go back to our matrix equation, what are we going to do to get the x by itself? Multiply both sides by a inverse. Now, unlike real numbers, matrix multiplication is not commutative, right? So we have to be very careful about where we're putting our a inverse. So on the left-hand side of the equation, where does the a inverse go? In front of the a, right? So I have my a inverse. I have my a, and my x. And then where's my a inverse going to go? On the right-hand side. Right, we have to do it to both sides. Is it going to go before the b or after the b? Has to be before the b. Why can't it go after the b? Okay, it's before on the other side. There's another even better reason than that. What's the dimension of a inverse going to be? It's going to be a 2 by 2, right? Can I multiply a 2 by 2? Or can I multiply a 2 by 1 to a 2 by 2? No, the dimensions don't work out. So we have to be very careful that we're putting those, if we're multiplying on the left, both the multiplications go on the left. If we're going on the right, they both have to go on the right. You can't go like one on the right and one on the left. If that makes sense, I hope it did. Okay. So, if I multiply a and a inverse together, what do we get? Well, not 1, because these are matrices, but it's a matrix that acts like the number 1. It's not the 0 matrix. It was the multiplicative identity matrix that we call the letter I. And what do I get when I multiply the matrix I to the matrix X? Just X. Everybody okay with the algebra that we've done here? Okay. The 2 and this was just me making an analogy about solving this equation was basically the same idea as solving the matrix equation. I asked you guys what to do first, and nobody had a good answer. So it's like, okay, let's kind of draw something similar that I know you know how to do, and we'll kind of point you in the right direction. So let's go ahead and fill our values back in. So now I'm going to draw back in, or write back in our values for A and B, or XA and B. So far, so good. So the first thing I need to do is compute the inverse of A. So I'll take the determinant. So I have the determinant is -6, right? Oops, sorry, +6. That's -1 minus a -7, which gives me +6. Everybody's okay with that? Okay. And now I have to rearrange that matrix A. So the first and the last element switch locations. And then the other two elements we negate. So negative of a -1 is +1, and -7 or negative of a +7 is -7. Everybody okay with that? So notice the inverse symbol is gone because we've computed the inverse here. Now we have an option. Do you want to multiply the 1/6 into that first matrix, or do you want to multiply the two matrices together? Which one would be easier to do first? Well, what's the worst part about dealing with fractions? Probably having to add two fractions, right? Multiplying a fraction to a number is not a big deal, but adding two fractions is a little tedious. So if I multiply the two matrices together first, all the adding that needs to be done is going to be with the whole numbers inside the matrix, right? That's what I would do. Now, it doesn't matter. Let me be clear. It doesn't matter which one you would do, but goodness gracious, let's not make our lives any harder than they need to be. So I'll take the first row and multiply to the column. And I'll take the second row and multiply it to the column. And then I'll go ahead and simplify that. So -3 plus -3 is -6. Then -21 plus -3 is -24. And if I do the scalar multiplication then in, I have -1, -4. So what that tells me is x is -1 and y is -4. Yes, it is. So 1/6 times -6 is -1. And 1/6 times 24 is -4. Is that what you needed? Okay. So let's talk about what work I would like shown for a problem like this. We did more than I would expect you to do. So I would want to see the matrix equation. I'd want to see it rearranged to a place where it was solvable. And then I'd want to see like your solving steps. So I don't need to see all that matrix algebra in between because it's exactly the same every single time, right? Quick question on this. Where can we get in trouble with this? Everywhere? When I say in trouble, I mean run into a situation where maybe this stops working. Okay, if maybe you can't multiply the matrices together. But as long as my number of variables in my equation, in my system, and the number of equations in my system is the same, like if I have 2 variables and 2 equations, or 3 variables and 3 equations, as long as those match up, that can't happen. Everybody okay with that idea? And that's always been the case for us, right? We've never asked you to do like, give you 4 equations and 3 variables or something. But that's a good notion. The place where we can get into trouble is here. Why would the inverse potentially get us into trouble? Could put it in the wrong place, okay. Presumably we follow the same form, though, that wouldn't happen. That's something that's avoidable anyways, right? Sydney, you want to say something? Yeah, so if the inverse has a 0 determinant, it doesn't exist, right? Is it possible to get a 0 determinant in doing this? Let's look real quick. So look at this system for a moment. You should know the answer to this without even having to do anything. Okay, so this system has no solution, right? If we tried to set this up as a matrix equation, we'd have this, right? And then we rearrange to say this, but this doesn't exist. Because its determinant is 0. Right? Similarly, if I had something like this, what's the answer to this going to be? That's going to be infinitely many solutions, right? Because the 2 equations are essentially identical, right? One is just a scale multiple of the other. The same thing's going to happen, though, if I try to do the determinant. I get a 0 determinant there. So this matrix equation kind of falls down if we run into a situation where there's no solution or infinitely many solutions. It's not going to help us identify that. Nor could it help us tell the difference between the 2. Now, in a 2-variable system, it's very easy to tell whether it's no solution or infinitely many solutions just by kind of looking at the equations, right? Remember, though, in the 3-variable situation, that didn't have to be the case, right? The 3-variable system, sometimes there was no obvious, like, oh, one equation is just a multiple of the other, or they're like the same thing but on the left, but they're not the same on the right. That it was, in fact, some of those, it wasn't even, like you couldn't look at it at all and make that decision. So this has an obvious drawback. Okay, well that's bad. Let's look at the next method. Maybe that one will be a little bit better. Okay. So we're not going to derive the formulas that I'm going to present here. So let's explain what's going on here, because again, the formula is a little bit complicated looking. Visually, though, it's an easy formula to remember. So if we're solving for x, I'm going to replace the x column of my coefficients matrix with the solutions. Everything else in the coefficients matrix stayed the same. If I'm solving for y's, I'm going to replace the y column. Change that color. In the coefficients matrix with the solutions. Everything else stayed the same. And this scales quite effectively to however many variables and equations you have in your system. So for example, if we have a 3-variable system, okay? So the denominator for each of these, you know what, let's move this around here a little bit. I'm going to get myself into running out of space if I do it that way. Do it this way. The denominator for each of these is going to be the same. It's just the determinant of the coefficients matrix. That's always the case. Everybody okay with that idea? So that's easy to remember, right? This is the coefficients matrix is the same. We built that the same way that we did when we did the matrix equation. The coefficients matrix is easy to see. It's just exactly the format of what's up in the original problem, right? Okay, so if we're solving for x, instead of writing my column for the x's in my coefficient matrix, I'm just going to write the solutions column. And then everything else stayed the same. Everybody's okay with that? I'm going to solve for the y's, the y column becomes the solution column, and everything else stays the same. Or if I'm solving for z's, the z column becomes the solutions column, but everything else stays the same. Is that okay? So again, the formula looks yucky, but when we explain visually kind of how we're creating that formula, it's like, oh, okay, like that's easy enough to remember. It certainly wouldn't require me to memorize the letters, right? Because that was a lot of letters going on in a lot of different orders. Okay. So drawbacks to this, as the system gets bigger, the determinants get more difficult to do. For example, in this 3-variable system, you have to do 4 3x3 determinants, which is a little time consuming. What's going to happen if we have, or where can we get into trouble here? Where can this method fail? Let me put it that way, maybe. Maddie? Which determinant? Not any of them. Not any of them. Well, in fact, if I have a determinant, not a big deal, right? 0 over any non-zero number is just 0. What can get us in, or what can cause problems for us, is if the denominator is 0. When will this happen? That happens in the no solution situation and in the infinitely many solution situation. That's a bummer. Yes. So the determinant is just a number, like 7, right? So there'd be like number over number, that's your answer. So you'd actually have to compute those 4 different determinants, but then you just have a fraction, right? So it'd be like 10 over 2, 8 over 2, and 6 over 2 or something. Okay with that? Okay. So as far as like a test goes or whatever, the work that I would want to see is simply just the setup for something like this. And then whatever matrix arithmetic you need to do to kind of get the answer. Depending on the directions on what I'm allowing you to use, right? Like if I say you can use your calculator to do the matrix arithmetic, really you have to write that down and then like the answer afterwards. It's not really much to do. The last one that we want to talk about is Gaussian elimination. So let's look at an example here. 19. And the last one is a negative 20. So to set up Gaussian elimination, what we're going to do is we're going to make one matrix where each coefficient is one entry in our matrix. Now it's important that only the solutions are on the right-hand side of our equations. So the solutions must be the last column in our matrix that we're making here. Just as an aside, this is called an augmented matrix. And our goal is to do stuff so that the left-hand side of our augmented matrix looks like the identity matrix. And then the right-hand side of our equation will give our answer for x, our answer for y, and our answer for z. Is what's going to end up happening. And I'm not going to show you exactly what's going on here because I'm not going to ask you to ever do this by hand. But I do want to give you a brief explanation of kind of what the calculator is going to be doing when it does this, so that it's not magic. And you have some sense of like, okay, the calculator is just doing like all of these steps, and it's doing a lot of steps, but it can do them very, very quickly because it's a computer, and computers are good at doing like following instructions very fast. Okay? So this step in here that I've written, this is like the Gaussian elimination that's going on. That's taking our beginning answer to this final answer. This final answer is row reduced echelon form, or RREF is the abbreviation we most often use for this. Okay. So the Gaussian elimination algorithm, basically this is what it does. So first thing you do is you multiply row 1 so that the first entry is equal to 1, assuming that the first entry isn't 0 already. So for example, in our matrix, we would do -1 times row 1. And we're going to store that answer into row 1. So we're going to replace our existing row 1 with -1 times row 1. Everybody okay with that notion? Then we're going to add a multiple of row 1 to rows 2 through whatever, so that the first entry cancels. And then we're going to store that back in to row 2 through. So in our problem, I would then do like -4 times R1 plus R2, and that'll get stored back into R2. Mia? So row 1 now starts with a +1. So +1 times -4, when I add those together, would cancel out the +4 there. Okay with that? So it's just like the elimination that we did by hand, right? It's just now we're programming this into a calculator to do it as a matrix. And then we continue doing, so we did all of that. Then we're going to multiply row 2 so that the second entry is equal to 1. And then keep on going. So we'll do that. Then we'll take multiply that row 2 by some constant so that when we add it to the row 1 and row 3, it cancels out the second entry, and we store those into their locations. And we keep doing this until we've done it for every row and every column, and what you're going to be left with is something that looks like this. Okay? Again, never going to ask you to do this by hand. Never going to ask you to tell me what the steps are. I'm just kind of explaining to you what the calculator's doing so that when we use the calculator, it's not necessarily magic. Okay with that? Okay. Here's the takeaway, though. Using Gaussian elimination, we can tell the difference between no solution and infinitely many solutions. And even better, we can generate the parametric solution in the infinitely many solutions case. Which is pretty rad. Okay. So it's time to take out our calculators because we're about to do some examples of these methods using our calculator. Calculator with you, or you prefer to just sit and watch? That's okay too. Of course. So I'm going to write down a system here. And it's the same system that we just looked at a moment ago. So if it's still right there on your paper, You don't necessarily have to recopy it, but I'm just going to write it down again. So we'll do this with a matrix equation to start with. So we'll start by writing a matrix equation. Even if I asked you to use your calculator to do this, I would expect to see this step for the setup. And then we do some matrix algebra. And this is what we're going to type into have our calculator do for us. Notice that at no point in this course have I asked you, or have I told you how to do a 3 by 3 inverse. You're not capable of doing that by hand. That's okay. The calculator is going to take care of all of that for us. So let's talk about how to get this into our calculator. So the main place that we're going to be using is the matrix menu in our calculator. So if you notice above the x to the negative 1, that's the fourth button down on the left, is the word in blue that says matrix. So if we press the second button and that x to the negative 1 button, that opens up the matrix menu. Now I have some matrices already in here, so you can see that my dimensions for some of these have already been set. If this is the first time you've entered the matrix menu, yours are probably all blank. To enter a matrix into our calculator, we're going to go over to the Edit tab, and I'm going to edit matrix A. So the first thing we'll do is set the dimension. So this is going to be my matrix A, this coefficients matrix, so it needs to be 3 by 3. And then I'm just going to type in the entries in my coefficients matrix as they're written down on my sheet of paper, just pressing enter to move from one entry to the next entry. Any questions about what we've done so far? So you just select one of the matrices to edit, A, B, C, whatever. And then you'll get right into this screen. And you'll just change the dimension to be 3 by 3 and type in the entries exactly as we wrote them down on our sheet of paper. Once you've done that, we're going to exit out of here, go back into the matrix menu, back to the Edit tab, and this time we're going to pick matrix B, and we're going to do that for the next matrix, which would be a 3 by 1. So that's our solution. So 2, 19, and 20. I'll pause here and give everybody a chance to kind of catch up. So you press second and mode to exit to the main screen, and then you press second matrix again, go back to the Edit tab, and select matrix B. What's up? Are you okay? Yeah. I know that you're gone and you missed a little bit, so if you need a little catch up, I can help. Okay. Is anybody still typing? All right. So I'm going to exit back to the main screen. So I press second in mode. Now I'm going to go back and I'm going to retrieve my matrix A from my matrix menu. So I'm going to press the matrix button. Under the Names tab, I'm going to select matrix A. And then I'm going to press the x to the negative 1 button, which is the same button that the matrix button is, right? Then I'm going to press the times button. Yes, Sydney? The 2, 19, 20, the other matrix that I'm going to, is part of my solution. Is that okay? And then I'm going to go back to my matrix menu. So I'm going to press second matrix. And this time I'm going to select matrix B. So what I have written on my calculator is exactly what's on my sheet of paper, because this is A and this is B. Then I'll press enter. Now this is clearly some fractions, right, what I've gotten here. So I can ask the calculator to give me this answer as a fraction. So if I press the math button and select the fraction command, it'll rewrite that as fractions for me. And that's what I won't need. So what this tells me is the matrix XYZ is equal to 10, 19 over 15, negative 11 over 3. So my answer is 10, 19 over 15, negative 11 over 3. Yep, so the inverse button is the same as the matrix button. You just don't press second. Sydney? Of course. Not bad, right? Not that bad. It's once you have your matrices typed in, you're putting it on the screen just like you would on your sheet of paper, right? So it's exactly what we write down. So let's do now this same problem using Kramer's method. So just like before, we'll start by writing down our fractions. Oh, well, okay. You want to start with the bottom? That's fine. No big deal. We can start with the bottom. I was just going to start with the top, but that's okay. No big deal. Okay. And then the top is going to be the same as the bottom, but instead of the x's in the x column, or what's in the x column, I'm going to write the solutions. Everything else, though, is going to remain the same. The denominator is always the same. Well, actually, I'm going to write something next to this. So let's do that. Again, the numerator here for the y's is going to be exactly the same as the denominator, but instead of the y column, we're going to write the solutions. So to type this into my calculator then, I'm going to press second and then the x to the negative 1 button. I'm going to go over to the Edit tab and I'm going to use the matrices C, D, E, and F. And I'm going to type in a 3 by 3 matrix for each of the 3 by 3 determinants that I need to take. So in matrix C, I'm going to choose to put in the coefficients matrix. And then I'm going to do X, Y, and Z in the next 3 respectively. So I'm just going to take a moment to type all those in. The only unfortunate part about this is that there's no way to just step back one menu. So once you finish typing in one of the matrices, you have to exit to the main screen to go back in to the Edit tab and go to the new matrix. Which is kind of a bummer, but, you know, not that big of a deal. We do need to make sure we're being careful when doing this. It's very easy to like make a typo, and that'll give you the wrong answer, which is kind of a bummer. So there's my matrix for x's. And we'll do the one for the y's. Oh my goodness, look at it. How stupid am I? What a big fat waste of my time. I wasn't looking what I was doing. I didn't have my dimensions set right, so I was just like not really doing anything. I was paying too much attention to making sure I didn't type in the wrong numbers. Put it into fractions. You can just, I'll show you in a minute how we're going to do the next step. Because we still need to take the determinants. Right, and I haven't mentioned how to do that yet. You know what I mean? Okay. Maybe you do know how to do, oh goodness gracious. Maybe you do know how to do the determinants already. Maybe you're a matrix wizard, which would be a pretty cool thing to be a wizard of. Okay, I've got all my matrices typed in. Is anybody still typing theirs in? Okay, we'll wait a minute or two. All right. So I'm going to go ahead and make my fraction. So to do that, I'll press alpha and the y equals button and choose that first option. In the numerator of my fraction, now I want to do the determinant of, in my case, it was matrix D. To get the determinant command, I'm going to press second and the matrix button. I'm going to go over to the math menu, and I'm going to choose then the first option, which is DET. Where at? So alpha y equals to get the fraction. It's the very top left corner, like where we graph. That's okay. And then you'll choose the first option. That gets you the fraction. And then you went back into the matrix menu to the math tab and chose the first command, which is DET. And now we're all caught up. Yep. I'm going to go back into my matrix now because I'm going to take the determinant of D, was where I put mine. And I'll move to the denominator. And here I'm going to do the determinant of. So back to the matrix menu, back to the math tab, choose determinant. And I'm going to go then back into the matrix menu and pick matrix C. And now that I have the determinant of D over C, I'll press enter to get 10. Now we have a couple of options here. We could retype that all in, and I have to go back through all those menus again. Or I can just edit this to replace matrix D with matrix E. That's what I'm going to do. So to get the last thing you typed back on a line that you can edit, I'm going to press alpha and enter. Yeah, okay. Sure. So we'll go back in here, and I'll move my cursor so that it's on matrix D. And then I'll just go back into my matrix menu and change that to E. And then press enter. And then repeat it one more time. Go in and change that to an F now. There's that. You know what this tells me, guys? This is the same system as before. Somehow we must have typed something. I must have typed something into our matrix wrong before because we didn't get this answer from the previous one. Oh, did we not put a negative for the 20? Yep, that's what I did it. So let's just fix that real quick. Thanks, dudes. Quotes. Yeah, what just happened? But last one is to do Gaussian elimination here. We save the fastest version for last. So I'm just going to do our REF of this matrix. We call this the augmented matrix, is the name we give this. So to type this in, I'm just going to go to Matrix, Edit. G is my next spot that I have open, so let's do G. This is a 3x4. And I'll just enter the entries in exactly as they're written down on my sheet of paper. And once I've done that, I'm going to exit out to the main screen. I'll wait for you guys to catch up when I get at that point. Everybody still typing? Okay, so what I'll do now is I'm going to go back to my matrix menu, back to the math tab, and I'm going to scroll near the bottom looking for the command RREF. Be careful because there's also an REF that's not what you want. You want RREF. So I'll press enter, and that puts it on the main screen. I'll go back to my matrix menu and retrieve my matrix G that I just made, and press enter. So what this matrix tells me is that this is equivalent to the system 1x plus 0y plus negative 2, 0x, 1y plus 0z, and 0xy plus 1z is equal to 3. And I typed something in wrong again. Ay, 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 folks. Or not. Oh, that's probably, oh. What the heck happened here? That's supposed to be negative 2 somehow. Not 10, apparently. Oh, I see what I did on the first one. I didn't write negative 20 there. And it carried from this one, where I didn't do negative 20, and it gave me 10 there. Boy, I am dumb today, guys. How come when you guys were getting the same answers I was getting, you didn't yell at me? So what this tells me then is just, there's my answer. Pretty righteous, huh? So here's the bonus. Now on your test, obviously I'm going to expect you're able to do some stuff by hand, but it's not like I'm not going to let you use your calculator. That system? No. Like solve a 3-variable system, like using substitution or elimination. You could start by just doing the Gaussian elimination, finding out what the answer is so you could know if you're making a mistake along the way, which is awful nice to know, right? Makes it that much easier to sift through your work to try to find a mistake. Let's do one more. Here I had said that one of the big pros for Gaussian elimination is that we're able to tell the difference between a no solution and infinitely many solution situation, and even give the parametric solution for an infinitely many solution situation. Let's do that here real quick, since these ones are pretty fast. So there's my system. Let's go turn that into a matrix. I'm going to put this in matrix H. So it's a 3x4. 2, 1, negative 3, 4, 2, negative 6, 1, negative 1, 1, 0. Nope. So 1, negative 1, 1, 0. Okay, so I screwed something up pretty massively here. It's supposed to be a 0. It's supposed to be 4, 2, -6. That one is 0. Okay. So exit out of there, go back in, and we'll do the RREF on that matrix H. And we get some goofball looking fractions, so we'll do math frac just to get a nicer looking answer. So what row of this is telling me that there's infinitely many solutions here? The last row. Very good. What does the last row say? Right, it says 0x plus 0y plus 0z is equal to 0. That's just like what we got when we did the regular elimination, right? Where we got 0 equals 0 at some point in the problem. You guys remember doing that? So this row, when it's all zeros, tells me it's infinitely many solutions. If I had something where it was all, I had 3 zeros and then a number, that would tell me that it's no solution. Okay with that? So if this was a number and everything else was 0 like it is there, that would tell us no solution. So to get the parametric solution, what I'm going to do is I'm going to use the first row, and I can write that as x plus 2/3 z is equal to 0. Notice that there's 0 y, so I didn't even bother writing them. If I subtract that, that's a minus 2z, or 2/3 z. If I add 2/3 z to both sides, I get that x is equal to 2/3 z. And then if I take my second row, I can do something similar. And I can write that y minus 5/3 z is equal to 0. And so if I add 5/3 z to both sides, I get that y is 5/3 z. Oops. And there's there's a parametric solution. Very easy to get that once from the RREF, right? Which is a pretty big bonus that we're able to get both of those things. Cool. So homework 10, I think, is what we're on. So here on homework 10, I ask you to set up and solve each of these systems using a matrix equation, using Cramer's rule, and using Gaussian elimination. And I ask you specifically to use your calculator to do the matrix operations. So all you're doing is just kind of like writing out the setup and then typing in your calculator to get the answer. You should get the same answer for all 3 parts, right? So it's a good check to make sure you did it correctly on your calculator. And keep in mind, I think that if it is a no solution or infinitely many solution situation, you're going to get errors for the matrix equation for the Cramer's rule. So I might, if it was me, I would start with the Gaussian elimination, because I could tell right away if I was going to get, if the other 2 are even possible. Mia? You should do the setup and say that it's no solution. Yes. But at least you're not banging your head against the wall going, why isn't this working? You know what I mean? Which is definitely something I can see us doing, right? But that's it for this one. We'll take questions on Monday. This is the last topic in this seemingly never-ending chapter. So we'll work on the review stuff next week, and talk about a test date either end of next week or beginning of the week after. Okay? Okay. Thanks, guys.
Mr. Cool.